Welcome back to the Professor Stu Boyce channel. I am Professor Victoria and this is Professor Corey, and today we're going to be talking about bond polarity as well as molecular polarity.
So before we start talking about polarity, I want to bring back this idea of electronegativity. And what we have here is we have the periodic table excluding the noble gases, and we have the elements in here, and these little numbers represent the electronegativity, and they've kind of color-coded them based on the size of the number. But what's really important is that the electronegativity scale goes from really close to 0 to 4. And 4 is the highest electronegativity we can have, and only one atom has an electronegativity of 4, and that's fluorine. You can see that in the upper right. And if you look, there is a general trend in electronegativity. It seems to be lowest in the bottom left and highest in the upper right. That seems to be the general trend. Now, what is this number? This electronegativity is essentially how badly does the atom want an electron. So fluorine would really like an electron. Its valence shell is close to the nucleus, so there's a strong pull, and that valence shell just needs one electron to have a complete outer shell in a noble gas configuration. So that's the basis of electronegativity. Now let's apply that to polarity.
Yeah, so if you are thinking about a covalent bond, so electronegativity is how strongly that nucleus pulls the electron within that covalent bond. So we're sharing electrons, and if you think of it as a tug-of-war, so each of the atoms has a strength and they're pulling on the electrons. I want the electrons closer to me. So if you picture like a diatomic element like this, we have fluorine. So they are the same atom. They must have the same, they have the same electronegativity, they have the same strength pulling on that bond. So the electrons are equally shared. So we call this a non-polar bond because the electron density, which is negative, is equidistant and equally shared amongst these two electrons. Now, if they're not the same atom, then there's slightly different electronegativity, then we would create what's called a polar bond. So we're going to picture that in this.
Yeah, so let's take a look at HF. Now, just from memory, I know H had an electronegativity of 2.1, and fluorine, of course, was 4.0. So fluorine has a stronger pull on the electrons. So they're sharing, but it's not really equal sharing. It's kind of like if two kids went together to buy a video game that cost $100, and one of the kids had $80 and the other kid had $20. The kid that only donated $20 would probably not get to use the video game as much. Well, likewise, the electrons are going to be a little closer to fluorine here because of that higher electronegativity. And this unequal distribution of those electrons is going to create what we call a polar bond.
So polar meaning different on each side. If you think of the poles of the Earth or the poles of a magnet, they're different. We've got a North Pole and a South Pole, and they're different. You can advance. So if we call this bond polarity, and there's a molecular polarity as well. So bond polarity, we have an uneven distribution of electron density that creates a larger density or negative density on one side to the other, so that's a difference. And to measure this strength, we call that the dipole moment when we measure that strength. It comes from a difference in electronegativity that we've talked about, and the electronegativity difference of 0 would be a nonpolar bond. Some of this is described, sometimes you'll see electronegativity differences of less than 0.4. Some texts will have as a nonpolar. We usually just consider nonpolar bond is just for those diatomic elements where they're exactly sharing the same, the electrons the same.
I think if we look at the electronegativity, we can get into some situations, like if you look at the hydrogen and the phosphorus, they both have electronegativity of 2.1. So a phosphorus to hydrogen bond would be nonpolar as well. We got tellurium. We've
There's
got
a few examples.
Quite a few at 2.1. The same with hydrogen, you might see, but most commonly for sure, the diatomic elements, of course, are going to have the same electronegativity on both elements.
Okay, so back to our hydrogen fluoride example here. We talked about how fluorine has the larger electronegativity, so it has a greater electron density around it from that within that bond as well as the lone pairs around it. But we use these little symbols to represent that it has a partial charge. So it's a covalent bond. It's not an ion where it has a full negative charge, but it has a partial negative charge, and then that means that the other side has a partial positive. We also represent polar bonds with this symbol here down in the bottom. So we have an arrow, and the arrow points to the greater electron density, and we put a little plus sign on the other side, which shows the side that has the plus side. So the partial positive is on that side.
So here's a question. We've got a series of bonded atoms, and we have to predict which would have the greatest bond polarity. Now, if you have your electronegativity chart, we could assign numbers to these. If you didn't have the chart, we could kind of use the trends to probably get through this. So we see the nitrogen and the oxygen are very close to one another, and they have electronegativity values that are pretty close. Now, potassium is a metal. It's way to the left and very low electronegativity to the fluorine. So the difference there is very big. Boron and nitrogen, again, pretty close in electronegativity. The same with the sulfur and the chlorine. So the largest difference in electronegativity is going to be the most polar bond. So our most polar bond is right there, our KF, and that's actually an ionic bond. And ionic bonds are always going to be polar. Interesting.
All right, so now we're switching to polar molecules. So the entire molecule, not just the bond. So for a molecule to be polar, we need to look at the shape. And if we have a shape that's asymmetrical, and then we can say this is a polar molecule. It might be a very slightly polar molecule depending on how the electrons are arranged and the bond polarities and such. So we can have a slightly positive and a slightly negative, or a very partial negative and quite partial positive as well for these molecules. But we're looking for shape. We're looking for the symmetry of the shape.
And some of these are really obvious, and some of them are not so obvious. So this one looks like it has 3 hydrogens that are just, symmetrically placed around the nitrogen. However, we have a lone pair of electrons in just one. In any molecule that has one lone pair of electrons is going to be a polar molecule. This has disrupted the symmetry. Now, if that lone pair of electrons was a bond to another hydrogen, then it would be symmetrical.
Right, and he's talking about just a molecule with one central atom when he made that statement. So again, we have this the ammonia here, and we're showing the bond polarity, how we have the arrows pointing toward the nitrogen. So the nitrogen is more electronegative. It's drawing those electrons, but it also has that lone pair. So we can see that the negative side of that molecule is pointing up toward the lone pair, and the positive is at the bottom. So we have partial positive, partial negative, polar molecule because it's asymmetrical.
So here's an interesting slide for 2 reasons. One is we just introduced this term dipole moment, and that just means is it polar? And the molecule itself is boron. This is the boron exception with 3 bonds. And oftentimes what students want to do when they're looking for symmetry is they want to try to draw a line through the molecule and see if it's the same on both sides. And we can't really do that. I guess technically we could, but this one gives students a lot of trouble because they'll draw a line through it like this, and they'll say, well, there's 2 fluorines on one side and 1 on the other, so this is not symmetrical, and that is incorrect. This is actually symmetrical. The space around the boron is filled with fluorine atoms, and since they're all the same atom, this is considered to be symmetrical, and this is a nonpolar molecule.
Yep, that positive side is all toward the center, and those negatives, that larger negative electron distribution is all around the outside. So the VSEPR model tells us that these are as far apart as possible. And so if you go forward one, if all occupied domains are the same atom, so we have no lone pairs, and all of the atoms that are around that central atom are the same, then you will have a nonpolar molecule.
That's a great tip. So here's kind of some steps. Some people like the steps, they want to have a series of steps. So this is how we're going to do it. We're going to start with the Lewis structure, and then we're going to determine the shape. We're going to determine the shape by counting the domains. Is it symmetrical in all directions? Does this mean, are the atoms all around the same atom? Like just noted, this would be nonpolar. Is it asymmetrical? If it has a lone pair, maybe it has an odd atom. Maybe it has 3 hydrogens and a chlorine as terminal atoms. This would be considered asymmetrical. This is going to be a polar molecule.
So here's a question. We have CHF3. We wonder if this is symmetrical. Take a look at it. If this is a tetrahedral, but notice how they're not all the same. Not all the atoms are the same around that central atom. We have 3 fluorines and 1 hydrogen. This is definitely an asymmetrical molecule, and it is polar. All right. This is another type of question that you might see.
So, we can look at these molecules, and it's really tough to predict without a Lewis structure. So let's go look at the Lewis structures first, and we'll see if they're symmetrical or not. So which of the following is polar? We're looking for the one that is not symmetrical, and that is going to be number 4, or CLF. They're pretty close in electronegativity, but fluorine 4.0 has got a higher electronegativity. There's going to be an unequal distribution of the electrons favoring the fluorine side of this molecule.
Here's your practice slide. All right, so you're going to want to draw the Lewis structure for all of these. Think about the shape and then think about symmetry. Do we have a symmetrical molecule? If it's symmetrical, then it's nonpolar. If it's asymmetrical, then you're going to label it polar. So we're looking for what's the electron pair geometry, what's the molecular structure, and then if it's polar. So we're kind of bringing back some of that molecular geometry from our previous video.
All right, so pause the video and we will give you the answers in just a second. Okay, so I just want to talk about water. And water is tricky. We do know that the molecular structure is considered bent because of the 2 pairs of lone electrons up there. But it appears to be symmetrical. If I drew my line down through the center, I'd say I've got a lone pair and a hydrogen on both sides. It's symmetrical. But what if I drew my line this way? Now I've got lone pairs of electrons and then hydrogens on the other side. So this is a polar molecule. This isn't an even distribution around that oxygen. We've got lone pairs that, they can appear to be opposing each other, like in this drawing, but they really aren't. Remember, this is a 3-dimensional structure. The tetrahedral structure is 3-dimensional, and it's hard to see on paper, but this is actually a polar molecule. So we like to use this Polar.
Play that in the pool.
Yeah, this is a game you play in water. Water is polar. Just, really drill that in. That's a pro tip. Water is polar, and you're going to see why that's so important in upcoming lectures.
Mm-hmm. Thanks so much for watching the Professor Stu Boyce channel. We appreciate it. And come back to the place to learn chemistry where you matter as often as you can. Have a good day. Bye-bye.